So today's lecture is about heating, cooling, and ventilation of electrical machines. During normal operation, electrical machines will tend to have their output of useful energy accompanied by energy that cannot be usefully utilized. This now takes the form of either heat losses or sound or similar losses of power and heat or power and energy. In today's lecture, we look at what happens in the machines when we have these heating losses and how to account for them and how to ensure that the machine operates safely with while taking into consideration the heating losses. This is because in the normal operation, an excessive rise of heat will lead to a deterioration of the insulation within the windings of the machine or within the components of the machine. In which case, if you have a breakdown, total breakdown of the components of the machine, you will then end up with short circuits and your machine will stop operating as it should. So let's get started. Now, in the case of any machine, during its operation, the input to the machine in the form of energy is equal to the output that you get, which is usually in the case of machines rotational, or in the case of transformers, an output voltage plus certain losses that cannot be converted into an output. This gives you your efficiency. So the ratio of output to input is your efficiency, and the difference between the two is the losses. Now, these losses in most cases take the form of heat or heat losses. Yeah. So as the machine operates, it will produce some heat, which then has to be dissipated to the environment. So the heat produced is equal to heat stored plus heat dissipated, right? All the heat from your losses is either retained within the machine, that is, the temperature of the machine will rise, and this is the form of stored heat, or it is dissipated to the environment, that is, it loses heat to the environment through radiation, conduction, or convection. Now, in terms of the heat produced, we can quantify that as Q. So Q is your heat loss. Now, if we take a certain period of time, let's say dt, a small period of time, the heat produced in that period of time will be equal to G, which is the mass of the machine or any part of it times the specific heat of the machine. Specific heat of the machine. What this tells us is that the heat that is stored within the machine depends on the capacity of the machine to retain that heat. And that is also proportional to the mass of the machine itself. So the specific heat, the amount of joules that are retained within the machine as it heats up, are determined by its mass and the capacity of the machine to hold heat, which is the specific heat of the machine. And those two, within the small period of time we are talking about, will lead to a change in temperature. So this is a small change in temperature, right? This is the heat stored within the machine, but at the same time, you have heat which is being dissipated. And that is given by S lambda times theta dt over the certain period of time. So the heat dissipated within that same period of time that we're talking about here is given by S, which is the surface area of the machine. So the machine has a certain size. However, the surface that is able to dissipate that heat by conduction, convection, or radiation is dependent on its surface area. Likewise, lambda is the emissivity of that surface area. So when you have a certain area, the outside surface, for example, how much of the heat that is at that point can be released into the surrounding environment, and at what rate can it be released? And that is your emissivity. So the emissivity times the surface area times your temperature rise, not just the temperature of the ambient surroundings, but the rise in temperature above or below your, below would be a negative rise, above the ambient surroundings. How much of that heat causes a temperature rise within the machine? So these main elements or properties of the machine are what determine now your heat loss, or how your machine will be able to balance the heat that is produced against the heat that is dissipated, with in turn the heat being stored, right? So let's look at a machine under heating. So a machine under heating. So a machine under heating is a machine that has started operating, and as it continues to operate, the heat losses gradually increase and it experiences a heating phenomenon, right? Now, from this expression, where you have heat loss over a small period of time, leading to a change in temperature and a certain dissipation of heat, that leads us to the following equation, which is theta, which is your temperature rise, is equal to theta m 1 minus e to power negative t over tau. This is a negative, plus theta I e minus t over tau h. I'll explain each of these in turn. So from this expression to this expression, by the way, you can get the derivation of that. It is available in the separate attachment. We won't go into it right now, but you can look at the derivation and how we got from here to here in the attachment to this lecture. So you have theta, which is your temperature rise. So the amount of temperature rise, the degrees over which the machine will heat up, are given by theta m, where theta m is the final steady state temperature rise. And this is defined as, if you give the machine long enough, how long will it attain at that particular rate of heat loss? How long will it take to attain a certain steady state temperature rise, and what temperature will that be? So that theta m is almost considered to be the maximum temperature that it will reach, where it attains a steady state of temperature. And at the point where it reaches theta m, you find that the heat produced will be equal to the heat dissipated, yeah, when it attains that theta m. Because as soon as heat is produced, it is dissipated. The rate at which the machine is emitting heat is equal to the rate at which the losses are being converted into heat. So that's your theta m. The other interesting component would be, let me just correct this, would be this figure, tau h. Now tau h is your heating time constant. Constant. The heating time constant, which is a time period in hours, is the amount of time taken for the machine to rise to 63.2% of its final steady state temperature. So time taken to attain a temperature that is 63.2% of theta m, the final steady state temperature. And it is given by GCP over surface area times emissivity. Now these mean that you have the properties of the machine determining the time it takes for it to reach its steady state temperature. The mass of the machine and the specific heat, the amount of heat that is stored, over the surface area and the emissivity, give you your time constant, the time that it takes to reach a certain percentage of theta m. And if you look at the equation that we have here, you will realize, of course, that it is an exponential curve, which will look like that. And here you have your 63.2% of the theta m, whereby 100% is theta m. It will be attained at this level. Okay, and because it is exponential, one time constant takes you to 63.2% from the starting point. The next time constant takes you to another 63.2% of the remainder, and so on and so forth, such that eventually you can reach there at infinity. However, due to the exponential nature of the curve, you can get a figure that is close enough to what we are talking about. Now, one interesting characteristic of this that you will notice is that the heat, the temperature as it rises, has a certain relationship with the specific surface area. Now, the heat itself, the heat that is rising, is proportional to the mass of the machine and its specific heat proportion. Yeah, the specific heat of the machine. So Q, as it rises in a cubic fashion. Write it down here. So Q rises in a cubic fashion. The reason for this is heat as it rises is dependent on the mass of the machine, and the mass of the machine is dependent on its dimensions. What are the dimensions? The dimensions are length, width, and height. That is, you have 3 dimensions. So as you increase the mass of the machine, you notice that you are increasing by powers of 3. However, in terms of dissipation, dissipation is proportional to the surface area, and an area increases in powers of 2. It is a squared relationship. Yeah, the relationship between the two is squared. So you will see that this theta m increases directly proportionally to the amount of heat, but inversely proportionally to the amount of surface area. So this is the size or volume or mass that determines the amount of heat that you have to dissipate, but the amount of heat that is being generated, but the dissipation depends on surface area. Yeah, so while this increases in powers of 3, this increases in powers of 2. So this will tell you that as the size of your machine increases, it becomes increasingly difficult to dissipate heat. So that means that large machines are less capable of dissipating the heat that is generated. So let's move this down. right? Now, as we continue to look at that, let's look at the machine under cooling. Okay, so the machine under cooling will behave similarly to the machine under heating, whereby you have a temperature rise or a temperature drop, and it is related to those factors in a similar exponential way. So you'll have theta, which is your temperature rise, theta C, which is your cooling time constant. Cooling time constant. Times 1 minus e to the power of negative t over tau c. That is your cooling time constant. Sorry, this was actually... And you have theta I e minus t over tau c. Right? So your cooling time constant tau may not be equal to your heating time constant. Okay. Right, so let's look at an example that will bring this all together. So that's our example. A 20 horsepower machine with those characteristics has a final steady state temperature of 40 degrees above the ambient, of course. The ratio of conductor losses to constant losses is assumed to be that, and the total losses of the machine at full load are 1800 watts. Calculate its 1 hour rating for the same temperature rise if the heating time is constant at... The heating time constant is 180 minutes. So in this case, we can see that theta m is equal to 40 degrees and tau h is equal to 180 minutes. In hours, that is 3 hours, right? Those are our first constants. Total losses at full load, total at full load will be given by conductor losses. Let's call the conductor losses C, plus the constant losses or the ion losses Wi. And we've been told the ratio of the two, Wc over Wi, is equal to 1.25, which means that your full load losses will be equal to, this is given by, it means that Wc is equal to 1.25 Wi. So that means that 1.25 Wi plus Wi is the total full load losses. And that gives us 2.25 Wi. Right? Now, here we introduce the concept of 1 hour rating. So the 1 hour rating, which you've been indicated here, is a rating whereby you run the machine at a higher maximum load for a short period of time, and you ensure that it does not exceed the maximum temperature within that period of 1 hour. So if, for example, your heat time constant is 3 hours, that means that it will take it 3 hours running at a normal rating of 20 horsepower. It will take 3 hours to reach its steady state temperature of 40 degrees, steady state temperature rise of 40 degrees. But if we overload the machine for 1 hour at maximum, such that it attains this same temperature within 1 hour, we will still be able to run it without causing damage, because we have not exceeded the temperature that is indicated. We are simply attaining that temperature at a much faster rate than would normally occur. So what does that mean for us? So it would mean that we have a certain rating that would be used. Instead of a 20 horsepower rating like this, you would have a certain rating, which is x times 20, that we can utilize the machine at for 1 hour, right? And during that 1 hour, we say that the machine, the losses in that machine, let's call them WFL2, the losses at that machine, this is additional load, is X over 20 or X20. Okay, so that additional load will be given by X squared, and X is because in a machine such as this one, you would have two sets of conductor losses that increase. So that is a squared increase in the conductor losses, X squared times W2 plus WI, the original WI, all right? This is not W2, this is WC. Okay. So in this case, WFL2 will be given by, because we know WC is 1.2 times WI, it will be X squared times 1.25 WI plus WI, which in turn gives us 1.25 X squared plus 1 WI, which are the constant losses. Now, we know that our maximum steady state temperature rise is proportional to our full load losses. So this means that our theta m at the second state is proportional to 1.25 X squared plus 1 WI, in the same way that theta m is proportional to 2.25 WI. So the ratio of these two, theta m2 over theta m, will be equal to 1.25 X squared plus 1 WI over 2.25 WI, right? So now in the case of theta m2, we want a temperature rise to the steady state of 40 degrees C. So our theta that we are aiming at in this second case is 40. We don't know what the 1 hour steady state rise will be. So we give that theta m2 times 1 minus e to the power of negative 1 over 3, which is our tau m. Rearranging that, we get theta m2 is equal to 40 over 1 minus e to the power of negative 1/3. Bringing out the calculator, we can then have 40 divided by 1 minus e to power negative 1/3. So that gives us theta m2 is equal to 141.11 degrees C. So if we were to run the machine at this rating, or rather at this kind of temperature, or rather horsepower, we would find that our temperature rise would be 141.11 degrees C. That's what this means. So now if we go back to our equation, let me remove the calculator. So if we go back to our equation, we said that theta m2, which is 141.11 over theta m40, will be equal to 1.25 x squared plus 1 over 2.25. This can be rearranged to give us 1.25 x squared plus 1 is equal to 141.11 times 2.25 over 40, which in turn gives us x squared is equal to 141.11 times 2.25 over 40 minus 1 divided by 1.25. So let's bring back our calculator. So this is 141.11 times 2.25 divided by 40 minus 1 divided by 1.25. That gives us a value of x squared for 5.54995, the square root of which is 2.3. So you have x is equal to 2.35, let's call it 6. So what is this x? This x is the value, the factor over which we can multiply 20 horsepower times 2.356. So we can run our machine at 20 times that, and it will be 47.12 horsepower. So for 1 hour, we can run our machine at 47.12 horsepower, which is much, much higher than the initial 20 horsepower that we had. So we can afford to have a very quick temperature rise, and our steady state temperature rise for that would be 141 degrees, but we would only reach that for 1 hour. So after 1 hour, you can switch off the machine and it will not be harmed. You will have operated it as if it was being operated in the normal way.